I'm going to talk about applications. So my research has to do with looking at how we can use these new additive processes to build basically parts out of titanium for the aerospace industry. For Boeing is who we're working with. They want to see how we can use it. But I'm interested right now, that's way off in the future kind of, because there's no metal printed parts that are flying currently. Only plastic parts are flying. I actually read a report that over 30,000 parts in Airbus aircraft and over 10,000 parts in Boeing aircraft, including military. The fuselage of the Raptor is made out of printed plastic. So I want to look at polymers in aeronautics and also astronautics. So we're going to look at BAE Systems and then NASA. So BAE Systems is a British multinational defense, aerospace, and information security companies. Second largest in the world according to their revenue, which as you can see that's actually 16 billion pounds. Worldwide company, 84,000 employees, headquartered in London. So yeah, they look at civil, military, aerospace. So you can see there the Lockheed Martin Lightning II F-35. That is the basis of all, basically, fighter jet for the United States and the UK in the future. It's based on the X-35 Joint Strike Fighter. Many of you probably don't know about that, but it can land and take off vertically. There are different variants used for aircraft carriers. So they make that. They're involved in that. They're involved in the Eurofighter Typhoon. They're involved in the Astute type submarine, which is a nuclear type new stealth submarine, and the Elizabeth class aircraft carriers, which is the newest type of aircraft carrier. So they do a lot of this type of work. So what they did was they looked at a really small component called the breather pipe. The breather pipe is part of this British Airlines 146 regional jet. There's 500 of them that are in service, so these are small commercial airliners. And this breather pipe is a critical component of the window, and it basically regulates the air so the window doesn't mist. And although it's a small component, it's pretty critical. So if it was missing or not working, they would still have to ground the aircraft. So you can see it's not very big, 3-4 centimeters tall. This is the design. Air flows through. And again, it was made using nylon. From my understanding, there were flame retardant variants, glass-filled variants for prototyping, and it was made using an EOS SLS machine. I think the largest they made. Yeah, that's the machine right there. It has a production volume of 700 cc per hour, and again, the tensile strength for the AM is pretty comparable to the injection molded. So it's basically, this was a spares support application. So basically, they make these plastic parts, they've injection molded them, but the tooling has gone old, and to replace it will take a really long time. So their planes are sitting on the ground, and it was very expensive. So again, this is a critical part, even though it's a small part. It was beneficial, like I said, because of tooling. They avoided tooling completely. Build cycle was shortened by 83%. So they went from producing it in 6 months to 4 weeks. And they reduced the cost per part by 60 cents. So the original pipe, also, it helped in redesign. So one of my parts of my thesis is that we're looking at how parts can be redesigned and how these new additive technologies can be used to create new manufacturing plans. So even in this part, they could redesign. They made the pipe diameter, remember around that bend here, they made the diameter a little bit bigger by not increasing the external dimensions, but just the internal ones. That's something additive can do. And they also, I think, made that sharper turn a little less acute. So certified. So the European Safety Agency in Aviation, they're a little bit ahead of the Americans, but it's already been certified, so that was another benefit. The biggest thing is that the build cycle is shortened. So if you're able to shorten your cycle, you have more room for other capacity to increase your profit that way. So you're looking at cost savings. Maybe you see the 23,000 doesn't seem big to you, but if you look at the bigger system or the organization, it may lead to more cost savings overall. And like I said, the injection molding, they were going to have to spend so much money on it. It was a plastic part used on aerospace application. Now we're going to look at NASA, specifically desert rats or research and technology studies. So this is basically a group of NASA scientists, 100 plus, industry members, academics from all around the world that gather for 2 weeks every year in remote areas, primarily northern Arizona. As you can see, the Black Point lava flow in the desert there to the north of Flagstaff. And they're basically, what they do is they spend time out there developing tools like hardware, robotics, machines, and also skills. So operational knowledge about living in the desert, things like that. So again, they look at space exploration vehicles. So that's what my case study right here is looking at. They printed about 70 parts of this new generation rover for Mars. This is Robonaut, so robonautics, so using robots to do primary work on extraterrestrial surfaces. These two pictures are actually from my visit to the Lyndon B. Johnson Center, where they were working on this at the mock-up facility. This is a habitat demonstration unit, so they live out there. Commercial crew spacesuits, new type of spacesuits for different environments, asteroids, Mars. The Mars. Right, so operations, communication. So again, this is the SEV, the Space Exploration Vehicle module on display. These are pictures I took. This is the front little pod, and these engineers or astronauts, 2 of them per pod in a pressure-sealed environment. This is about the size of a Hummer, are sitting in here, and this pod can lower down. There's all types of robotic arms. This guy attached could either be another guy, another human, or a robot itself. Again, so these parts are made out of ABS, polycarbonate ABS mix, actually, using FDM. And it's, again, using the Stratasys Fortis, their biggest 900 MC machine. This is, okay, so this is actually an example of a part. So this is like an ear-shaped type cover, and it's very complicated. You really can't make it using traditional methods, and it's only one of 70 parts printed. So you can see it's in operation, and that's where the part is on the actual vehicle. This is another example of another part they made, just another type of fitting or bracket. Yeah, and so the tensile strength, not as great, but it's still comparable, and it suits what they need. I mean, it's very durable to last on another planet, so I don't... Video. Let's skip to the interesting part. Right, so 70 parts on board. And it's this vehicle right here. And this is actually them out in the desert.
Never released any spacesuits.
This is what they do. I mean, this is they do all this testing. Yeah, so this is that vehicle actually, and so it's about to go through this video and highlight some of the parts. Here we go. Is that part? That part? It's an actual door. Yeah. That. You saw that. All of this was printed. Yeah, I thought that this is a pretty big part, yeah.
It feels like they're reaching.
Yeah.
We printed this part.
A lot of this interior bulkhead.
Yeah.
Like I showed you this fitting from earlier. I think some of these camera mounts up there, the light mounts. Right, so here's some more Stratasys marketing.
A little bit better than mine.
Right, but this is with NASA, a little bit more involved, so that lends it a little more credibility than these skis are good. But
Isn't that one video where they first introduced this, where it like dries up, and then somebody comes up behind it, they're waiting to parallel park, and it just goes sideways and parallel parks?
I don't know. Yeah, I don't know if it was this one because the wheels you see can they can
like
retract. Again, so this is for a next generation rover because they need to simulate the brutal terrain, the environment. It's Hummer-sized vehicle, pressurized cabin. Again, it's ultimate utility vehicle. AM was beneficial because you could do design flexibility, so there were complex parts, there were customized features, right? If you're building this very customized vehicle, you want to be able to change your design constantly or make it very durable. You want to make it really easy, very fast, and you also don't want to cost a lot. And also material control, so if they're designing for certain environments, they want to be able to really specifically control the material chemistry or make it lightweight, flame retardant as well, so all types of things. Alternatives. Yeah, sure, some of the components could have been made traditionally, but that means it's going to take a lot longer, and there's going to be less flexibility during design. And also, some of the critical components, like I showed, that ear thingy, it was impossible to make traditionally, and it was also very expensive if they wanted to do it that way. So there's the SEV.